sure y'all saw the email. Not a whole lot of you are visiting office hours as it is, but this week they're going to be from 9 to 9:45. Nothing I can do about it. I've got training stuff, departmental stuff, so my apologies if that's inconvenient. We're going to finish up chapter 16. I'm going to subcontract out some graphics to your book because I'm not an artist as it is. I really can't draw this stuff. Chapter 16 is all about electromagnetic waves. We started talking about that on Friday. I introduced you to the electromagnetic spectrum. We're going to get back to talking about that. Chapter 16, though, starts off in kind of a strange way. It makes sense if you see where they're going, but what I want to show you is this idea of Ampere's law. Now, unfortunately, we did not really get into Ampere's law as much as I would like to. It just happens as the class goes on. We gotta list some stuff out. But Ampere's law is this: B dot ds, the closed integral around the line ds, right? Well, it would be the line s after you integrate. That is to say, there's some closed line that bounds a surface. Just like with Gauss's law, there was a closed area that bounded a volume, right? This is a closed line that bounds the surface. And Ampere's law says B dot ds is equal to mu naught I enclosed. Remember, the book is leaving off the enclosed. But that's what it is. It's the amount of current enclosed by this line. So the top expression of the brackets is mu naught is Ampere's law. The reason they're putting this in brackets is because they're talking about this specific surface. So you might recognize what this is as a parallel plate capacitor, right? That's being charged. So it's being charged, so there is current flowing, I, right here. So current is flowing onto the plate. We know how capacitors work. The current flows onto the plate. It builds up an electric field. It kicks charges off of this plate because they don't want to be near these like charges. And the current continues to flow down the wire. We talked about this when we talked about capacitors. You can kind of think about that the current is flowing straight down, but it's really not because there's a gap here, right? A capacitor is filled with something that doesn't allow current to pass, be it a vacuum, be it air, be it a piece of Teflon, whatever. It doesn't allow charges to flow. So this actually leads to a really strange thing because we presented Ampere's law as a fundamental law. But if it is, we have a problem here. So this dashed line is the surface in question that we're going to integrate over. It might be a little hard for y'all to see. We've got two different shadings here. This line bounds this planar surface S1, right? But a line, a closed line, actually bounds an infinite amount of surfaces. You can make those surfaces all cattywampus however you want to. As long as they're bounded by the line, it's a bounded surface. And so they've given you another, this is kind of this purple or magenta shaded one that comes down through the gap. Right? And so this is an interesting problem because there's clearly a current flowing through surface 1. But there's clearly not a current flowing through surface 2. The surface 2 passes through the gap and no charges are flowing there. Right? There's just a field that's changing. I should point that out. The field is absolutely changing in there as you're building up charges on this top plate thing. So S1 is the surface through which current is passing. That's what they say. Ampere's law, which says closed integral B dot ds equals mu naught I enclosed if the surface S1 is used because I'm enclosing a non-zero current, no problem. But then if I use the surface S2, which is bounded by the same line, I get an answer of 0 because there is no current enclosed. That shouldn't be the case if Ampere's law is a fundamental law. So, what to do about this? Well, if you've read anything about electricity and magnetism, the name James Clerk Maxwell should have come up at some point, right? In fact, most of the stuff we've been looking at, we can summarize, and we will in a second, by calling them Maxwell's laws. James Clerk Maxwell was a Scottish physicist, natural philosopher, he would have called himself, that did a lot of work with electricity and then afterward that magnetism. So the reason we understand electricity and magnetism as we do is mostly because of the work of James Clerk clerk Maxwell, who worked to synthesize all this stuff. So this is actually Maxwell's big contribution. Maxwell realized that this has to be wrong, and so how to fix it? So we fix it by postulating that there's something occurring in the gap that is like a current. It's definitely not a current in the sense of charges flowing per unit of time. dq dt is the definition of current. So we can't say that it's a current in our other sense, but we can say that there's something happening there that's like a current, so that Ampere's law can be rescued from being ridiculous, right? Because it has to work in all cases if we're going to call it law. So he postulates this thing that he then calls the displacement current. It's an unfortunate name because it makes you think that it's another kind of current. It kind of functions like that, but it is not, in fact, a current. It's something that we think of maybe fulfilling the role of a current. It's called the displacement current. Most advanced textbooks will use the capital D for that, or they use the capital I for current. We're not getting so far into it that we actually even need a symbol for it, but that's what it is. So what does that look like? Well, this is what he postulated. The displacement current, I hope you can see this, is equal to epsilon naught, and then look at the derivative there, d phi e. That's the electric flux. Electric flux through what? Through this surface that's passing through the gap, in this case of that capacitor. Doesn't have to be that particular surface. But whatever surface you're talking about, there is an electric flux, right? So that's why the charges are leaving the bottom plate as it is. Let me scroll back to see it. Okay. The reason charges are leaving this bottom plate is because there's an electric field which is kicking them off. The reason more and more charges are leaving is because as I put more and more charges on the top plate, that field is changing. It's getting bigger, in fact. And so it's kicking more and more charges off. So if I have a changing electric field, any surface through which that passes will then thereby have a changing electric flux. So we've seen a lot of stuff with changing magnetic fluxes, right? This time we're seeing a changing electric flux. So the change of the electric flux, I should say the time derivative of the change of the electric flux through that surface gives us this idea of the displacement current. We've got epsilon naught there. Should not be a surprise. This is my electrical permittivity. This is basically the constant that comes with any electrical phenomena, just like mu naught is the constant that comes with any magnetic phenomenon. These are the fundamental constants associated with both of those fields. So I've got this displacement current, right? So then I can put all that together. If I go back up to where Ampere's law is stated here, I can put these two ideas together and rescue Ampere's law, which is Maxwell's great contribution to Ampere's law, by reformulating Ampere's law here. They're going to formulate it a little more cleanly down here. But this is the idea. This is Maxwell's statement of Ampere's law. Closed integral B dot ds. B passing through some surface bounded by some line over which we're integrating is equal to mu naught I. That works just fine if there's an actual current passing through it. Plus epsilon naught mu naught. We'll talk about where that comes in just a second. D phi e dt. So this is the displacement current. So if there's an actual current, this displacement current would be 0. If there's not an actual current, this term would be 0. Where the mu naught comes in here is if I define the displacement current as this epsilon naught d phi dt, and then I recognize I've got to multiply it by mu naught, right? Just like I multiply this current by mu naught, I multiply this current by mu naught, which is why that constant appears there. Often people will factor it out to get mu naught times parenthesis I plus id, displacement, close parenthesis. However you write it, it's fine with me. The point is, this leads to a really, really important result. And this is as far as we're going with it. We're not going to work any problems with this. If you take advanced E&M courses, you'll work a lot of them. So if you're sad about that, don't worry about it. You'll get there eventually. But the point is, this magnetic field arises in the gap of that capacitor because there's a changing electric flux. So I'm going to say that again. The magnetic field in the gap of that capacitor and in all other gaps where we might find it arises because there is a changing electric flux through that gap. Okay, so what does this mean? Well, talk about what it means. Let me just go down to the bottom of this page, where your book handily collects what we generally call Maxwell's equations for us, which are right here. So this is a set of 4 equations. This is actually, if you're into sort of the elegance of physics, this is a beautiful statement. Really no other discipline besides electricity and magnetism can you sum it all up with such a succinct set of equations. There are 5 equations here. The top 4 we call Maxwell's equations, and then there's the Lorentz force law down on the bottom, the F equals QE plus QV times cross V. This is electricity and magnetism in a nutshell. I happen to think it's quite beautiful and quite elegant. There's a lot of work to be done in unpacking this. You can also, these are in these are in integral form. You can also formulate them in differential form, but they're the same equations. So this is what we call Maxwell's equations. Really what Maxwell did is synthesized them all and then added the term to Ampere's law, Gauss's law for magnetism, which we did not talk about, and we're not going to. Faraday's law and the Ampere-Maxwell law. This is the set of equations which basically describes electricity and magnetism. But here's the point of this discussion. Faraday's law is here. We studied that a bit. This is electromagnetic induction, right? What we decided, well, what this says is that a changing magnetic flux induces an electric field. We looked at it in differential form, right? We said script E, which is our EMF, is equal to minus N d phi dt, right? What they're doing here is recognizing that a voltage, our EMF, is also expressible in terms of an electric field, right? That shouldn't be surprising. A voltage gives rise to an electric field, bar none. If there is an electric field, there is a voltage, or I should say there's a potential difference. You don't get one without the other, right? So in this form, we see something really interesting. A changing magnetic field always produces an electric field. That's what Faraday's law says. A changing magnetic field always produces an electric field. Now, Ampere-Maxwell says the same thing in obverse. A changing electric field always produces a magnetic field. This is the key that puts these two ideas together. We started out talking about electricity. Then we talked about magnetism. We really can't, if we're going to be global about this, talk about one or the other. We have to talk about both. Which is why I've started using the word electromagnetic. Right? These are two sides of the same coin. You don't have a changing magnetic field without an accompanying electric field. And now it turns out you don't get a changing electric field without an accompanying magnetic field. You can't get one without the other. These things always come together. You might not care about one, your experiment might not worry about one, but it's still there. Okay? So, that's as much as we're going to do with the Ampere-Maxwell law. Unfortunately, there's a lot to be done, but it's okay. The point is to see that these things are intimately connected. They function as two sides of the same coin. Any questions about that? All right. Keep that in the back of your mind as we go forward. So, let's imagine that I have a conducting rod, just a piece of metal, right? And I'm going to take a charge. We all know it's an electron, right? That's what moves in metal. But let's just, for the sake of argument, not worry about that. Let's just say that it's some charge, and we'll say it's even some positive charge. And I'm going to require that positive charge to oscillate up and down that piece of metal. So this thing moves. I'm drawing it off to the side so you can see it, but it's just moving up and down the piece of metal, right? Oscillations are a thing we're somewhat familiar with. So, is there an electric field associated with this charge? Not a trick question. Yeah, it's a charge. If there's a field, there's a charge somewhere producing it, right? So yeah, there's an electric field. Now, let me ask you this. Is the charge in motion? In other words, does it have a velocity? Yeah, it's moving up and down. So I've got a field from the charge. I've got a moving charge. What do moving charges produce? Magnetic fields, right? Now, not only do I have a charge, not only do I have a moving charge, I have an accelerating charge. Hopefully we can all agree with that, right? At one point it's going up the rod, at another point it's going down the rod. I don't know how I can change directions without accelerating. It's also changing speed. It has to do that, right? I've got an accelerating charge. So it produces an electric field, it produces a magnetic field, and what I said last time, an accelerating charge is going to produce both of them in such a manner. An accelerating charge produces changing E and B fields. In point of fact, the E and B fields are going to oscillate just like the charge is oscillating. This is, to give you a spoiler alert, an antenna. It's just an antenna. It could be an antenna on a radio. It could be the sort of coiled up antenna inside your phone. It could be a very large transmission antenna for telecommunications. This is how antennas work. Charges oscillate. They oscillate along a piece of metal. And they produce changing electric and magnetic fields. Now hopefully with what we said a while ago, you recognize that these have to come in pairs, right? If I'm changing an electric field, I get a B field. If I'm changing a B field, I get an electric field. It doesn't really matter where you start. It's a chicken and egg thing. You get them together no matter what, right? There's not a chicken without an egg, and there's no egg without a chicken. There's no E field without a changing B field. There's no B field without a changing E field. It always comes together. You can argue till the cows or till the chickens come home about which one comes first. It doesn't really matter. You get them together. Okay? Alright, what does this look like? Well, it turns out it looks really, really interesting. So I'm going to draw like let me just draw. I'll start off with one and then try to draw later. This is another thing where my graphics are going to fail me. So hopefully we recognize this as a sine wave. I'm going to let this represent the electric field as a function of time. And what this means is that if the E field is oscillating, that means it's oscillating in direction and speed. Not speed. Careful. Magnitude and direction. So at some point in time, I've got a zero field. Right here. There's a zero field. There's a zero field here. There's a zero field here. So on and so forth. So a little bit after that zero field, though, I get an electric field that looks like this. Remember, electric fields are vectors, and so what I'm doing is I'm going to populate the inside of this wave with some vectors. I get an electric field that looks like this. It's pointed up, and it's increasing. A little bit later, I get one that looks like this. It's pointed up. It's bigger than the first one, and it's increasing. Here it's going to reach a maximum. What is the word for that in our wave language? What characteristic of the wave is that maximum there? You know, this is 5th grade science stuff. Is it amplitude? Thank you. Yeah, it's the amplitude of the wave. Don't let the fact that we're not talking about a wave on a string or a water wave confuse you, right? That's probably what the issue is. These are waves we don't see in real life. We see waves on strings. We see water waves. We don't see an electric field oscillating back and forth. But this is a wave, right? I'm graphing this in the middle of a sine wave. Yeah, that's the amplitude of the wave. Okay? A little bit after that, it starts to come back down, and then finally it reaches the 0 point here. And then it switches direction and does the same thing. It again reaches its maximum value, which is the amplitude of this wave. Don't let the fact that this is pointed down confuse you. The E field vector has switched direction, but by magnitude, the amplitude is the same. Comes back up, and the same thing happens ad nauseum, etc., etc. Okay. So this is what I mean when I say the E field is oscillating. It is changing in magnitude and direction in such a way that it is describable by a trigonometric function. Well, if that's true, I've got to get a B field that does the same thing, because how the electric field changes determines the B field. So if the electric field, remember what that equation said, B is equal to epsilon naught d phi dt. D phi is increasing when the electric field increases. Therefore, the magnetic field is increasing when the electric field increases. As the electric field decreases, d phi is negative. D phi dt, I should